This is Dr. Arlo Kane. This is a mini lecture on inner product and length for linear algebra at the University of Notre Dame, spring of 2017. The dot product is defined for vectors in Rn. You might have seen this before in multivariable calculus, where you talk about the dot product of vectors in R2 or R3. So if x is a column vector with entries x1 through xn, and y is a column vector with entries y1 through yn, then the dot product of x and y is defined to be the transpose of x, written as a row, times the column y, which then gives you a 1-by-1 matrix or a scalar, which has the products of the corresponding components added together, x1 times y1 plus x2 times y2, all the way down until xn times yn. Just for some quick examples, if we were to compute the dot product of the vectors 1, 1 and 1, negative 1 in R2, we would see 1 times 1 plus 1 times negative 1 gives us 1 plus negative 1 equals 0. Similarly, if we compute the dot product of the vectors 1, 2, 3 and negative 1, 1 in R3, we would have the first product of 1 and negative 1 would give negative 1, the next product would be negative 2, the final product would be 3. Adding those together, we have negative 1 plus negative 2 plus 3 equals 0. Correspondingly, we have an example in R4, 3, 1, 4, negative 5, dot with 2, negative 5, 1, 1. The products are 6 minus 5 plus 4 minus 5, which you can see adds up to 0. So up at the top of the screen here, I've recorded the definition, the formula defining the dot product. And now I want to state and record some properties of this product that we can use for simplifying calculations and doing algebra with vectors and dot products. So for all vectors u, v, and w and Rn, and all scalars c in our field of scalars R, the following identities hold. The first is that u dot with v is the same thing as v dot with u. Now you can imagine that this is certainly true in the case when the dimension Rn, when the n is 1, we're just talking about R, and the dot product is simply multiplication of numbers, and we know multiplication is commutative. When n is greater than 1, it's given by the formula at the top of the screen, and you can see that x1, y1, if these two variables were interchanged, because multiplication is commutative, we can do that without changing the value. We can change the order of the multiplication all the way down the chain, and then read the expression backwards. We would have the result of doing y dot with x. So this property is pretty straightforward. It's also pretty clear that it distributes across addition, because when you add vectors, you add corresponding components together. So the fact that multiplication of numbers distributes over addition of numbers means that each of the little pieces of the dot product here would have this property, and then you're summing up things that have that property, so the whole thing has that property. Now this says it distributes from the right, but because of the first condition saying that the dot product is symmetric, we can apply number 1 to number 2 and end up showing that it's distributive on the left as well. The third property is sometimes called a homogeneous property of the dot product, that if you multiply a vector by a scalar and then dot with another vector, it's the same thing as doing the scalar product times the result, the scalar times the result of the dot product. So again, in terms of formulas, if you were to multiply all the components of the first vector by the same number, then that same multiple would show up in each one of the summands. And so you could factor that multiple all the way out in front, and you'd be left with that number times the dot product of the two original vectors. So again, because of symmetry from number 1, you can use property 3 and symmetry to show that the same would be true if you multiplied the vector w and then took the dot product with u. You'd still end up with the overall scalar times u dot w. Finally, we should observe that when you take the dot product of a vector with itself, what are you getting? Well, if x and y here are the same vector, then when we do the dot product, we're going to have x1 times itself, that's x1 quantity squared, plus all the way down to xn quantity squared. And if you have real numbers that are squared, they're all non-negative, so if you add them up, it's still non-negative. So the result of the dot product is a number, a scalar quantity, and it's greater than or equal to 0. Furthermore, the only way that such an expression would equal 0, if you have a sum of squares, the only way that that can be 0 is each one of the squares is 0. But if each one of the squares is 0, then the thing you're squaring had to be 0, in which case it means that all of the components of the vector you're talking about were the number 0, so u is the 0 vector. Now the length or norm of a vector is defined using the dot product, and it's given by the following formula. So if you're given a vector v with components v1 through vn, and you want to compute the norm, what you do is take the dot product of v with itself, that forms the sum of squares of the components that we talked about before, and then you take the square root of this number. So the square root of v dot with itself. Okay? This is the definition of the length or the norm of the vector v in Rn. Now why do we call it length? Well, again, if we were talking about n as dimension 1, so that v was just a number, you would have the square root of v times itself. Square root of v squared is the absolute value of a number, and that's just the distance that number is from the origin on the number line. Since we draw vectors from the origin out to a point in space, the length of the vector representing that number is simply its absolute value. Correspondingly, in dimension 2, we might have a vector v drawn from the origin out here to a point in the second quadrant. We can make it the hypotenuse of a right triangle with respect to our coordinate system. The length of this edge here is the absolute value of the first coordinate. See, the first coordinate in this example is -2. That can't be the length of something. The absolute value of -2 is the length of that edge. Okay? The absolute value of the second coordinate is the height of the triangle, and to compute the length of the hypotenuse, we would use the Pythagorean theorem. The Pythagorean theorem would say then the length of the hypotenuse is the square root of the sum of the squares of the lengths of the other two sides, and those lengths are given by absolute values. But when you do absolute value of something squared, it's the same thing as that something squared when you're talking about real numbers. So this formula from the Pythagorean theorem is the same thing as this formula, which is used to define the norm. So we can conclude that the norm does indeed measure length in the plane. Stepping up another dimension to R3, the same thing is true. If you had a point over here, which is a certain number of units in the x direction, a certain number of units in the y direction, and a certain number of units in the z direction, so this represents the tip of a vector in R3. If we were to compute the length of this line segment, we would want to compute the hypotenuse of this right triangle, whose base sits inside the xy plane. Well, the height of that right triangle is the absolute value of the third coordinate. The base of that right triangle, though, is the hypotenuse of another triangle, which is laying on its side in the xy plane, and whose height in the xy plane, or the sort of y direction component, is the absolute value of the second coordinate of v. The x direction part is the absolute value of the first coordinate, and so the hypotenuse of that triangle is square root of v1 squared plus v2 squared by the Pythagorean theorem. So then, tilting our head up and looking in the third dimension now, we would again use the Pythagorean theorem applied to this triangle, and we'd have to do the square of this quantity plus the square of this quantity, and then take the square root in order to get the length. So writing that out, if we do the square root of the square of the hypotenuse length of the triangle in the xy plane plus the square of the height of that triangle, then simplify, lo and behold, we get exactly the same formula, which is the square root of v dot v, measuring which defines the length or the norm. So really this formula that's in our definition is a way of generalizing the Pythagorean theorem to higher dimensions and encoding our concept of length. Okay, so now let's imagine for a moment that we have two vectors u and v which are linearly independent in Rn. Okay? N could be an enormous number. We could be talking about R 57,000. Okay? But what do we know about u and v? Well, if u and v are linearly independent, as we have assumed, then they are both not the zero vector, and they are non-parallel, and they span a two-dimensional subspace of Rn, namely a plane through the origin. If we move our camera in space so as to view that plane the same way we're viewing it in the plane of the screen here, we could see a figure just like this one. There's the origin, there's the vector u pointing out in some direction, the vector v not parallel to it pointing off in some different direction. And if we compute the difference of u and v, we get a vector emanating from the origin out this way. But remember, we can also visually translate the vector without changing its direction or length. And when you do, the difference vector slides up and forms the third side of a triangle. So if we imagine for a moment that triangle in front of us, there's some geometric information in it, namely the length of the sides, something we can compute using the length or the norm of vectors in Rn. But there's also geometric information in the angle between the vectors u and v that make up the sides pointing out from the origin. Okay. What we're going to do now is remember some trigonometry, namely the law of cosines. This relates the length of the sides of a triangle to the cosine of the angle between two of its sides, according to this formula. It's also a generalization of the Pythagorean theorem in a different way. So, generalization of non-right triangles. So, with the sides labeled as shown here, A, B, and then opposing the angle theta is the side C, the law of cosine says that the length of the opposing side C squared is equal to A squared plus B squared. That's like the Pythagorean theorem. But then there's a correction, and the correction is minus 2AB cosine of the angle between the sides labeled A and B. So if we apply that law of cosines to our triangle, where A is the length of U, B is the length of V, and C is the length of U minus V, which is the same thing as the translated version up here, then what do we get? Well, on the left-hand side, we'd have u minus v quantity squared. On the right-hand side, we'll have length of u squared plus length of v squared minus 2 times the length of u times the length of v times the cosine of the angle between u and v. So now let's note that the left-hand side of this equation can be rewritten using properties of the dot product. Indeed, the norm of a vector squared, remember the norm of a vector is the square root of the dot product of that vector with itself. So if we squared both sides of that relationship, we would write the norm of the vector squared is the vector dotted with itself. So here the vector we're applying it to is the difference vector u minus v. When we dot u minus v with itself, we can distribute using the distributive property of the dot product and the symmetry, the commutativity of the dot product. We can do some algebra. So we would get u dotted with u, the outer terms minus v dotted with minus v. The minus signs will reduce to a 1, so you get plus. And then we'll have u dot v with a minus sign and v dot u with a minus sign. And remembering that the dot product is commutative, so you can switch the order, u dot v and a v dot u combine together, so you get 2 copies of u dot v. So this belongs on the left-hand side of our expression obtained from the law of cosines. What about the, we can rewrite it a little bit to see some relationships, which is that, remember, u dot u is the norm of u squared, and v dot v is the norm of v squared. So if we match this left side here on here and compare it with the right-hand side from the law of cosines, we see some cancellation that can occur. namely the norm of u squared and the norm of u squared can be canceled from both sides. The norm of v squared and the norm of v squared can be canceled from both sides. And then after that, there's a negative 2 in common, both sides, which can be reduced away to 1. So finally, we end up with a rather interesting identity, which says that u dot v is equal to the norm of u times the norm of v times the cosine of the angle between u and v. So this is something really interesting. It says that this simple algebraic formula, which just u dot v, remember, is just the sum of the products of the numbers of the corresponding components added up together. That simple product has a geometric interpretation. It contains information in it about both the length of the vectors, and it also contains information about the angle between those vectors. So the next topic we'll be discussing in class is about orthogonality, and this is when two vectors have the property that the angle between them is, or not the angle between them, this has the property that the dot product of the vectors is 0, as we had in our examples. So what does that mean about the angle between those vectors? Well, when u and v are not the 0 vector, these quantities are non-zero, and so the cosine of the angle needs to be 0. And if you remember from trigonometry, the angle between 0 and pi, a potential angle for an angle between vectors, the angle between 0 and pi, which makes cosine 0, is exactly pi over 2, 90 degrees. So the dot product being 0 means that the vectors are perpendicular to one another in space. So if we go back to the beginning, our examples here, each of these dot products working out to be 0 means that these vectors are perpendicular to one another in space. That's fairly clear with this example when we draw a picture in the plane plotting 1, 1 and 1, negative 1. It's easy to see that they form a right angle, and you can believe that characterization. This one is a little less clear, but if you were to hold up the fingers of your right hand with your index finger pointing out in front of you, your middle finger pointing off to your left, and your thumb pointing straight up and down, you would form a coordinate system in space. And if you held up two pens, one that pointed from your knuckle at 0, 0, 0, out 1 unit in your index direction, 2 units in your middle finger direction, and 3 units in your thumb direction, you'd have a visual representation of 1, 2, 3. And you could construct a similar representation of negative 1, negative 1, 1, and confirm that they do at least appear to be perpendicular. But of course, once we go to 4 dimensions, we lack the ability to make models anymore of these images, and the dot product helps you to generalize this notion of geometry of length and angle to higher dimensions.